Yeah, feel free to ask your questions, and the online participants can just speak up and interrupt. All right, take it away.
Great. Thank you all so much for having me. I'm so excited to be here today to tell you about some of my recent work, as Ken said, on black holes and DCS Gravity. So this talk is going to be based on two papers, one of which we put out a couple months ago in PRD, and the other one which is going to be put out very imminently in the very near future. And this is a collaboration between myself, my advisor, Stefan Alexander, Greg Papadazzi here at NYU, and Nico Yunus from the University of Illinois. Okay, so I just want to give you all the main takeaways of this talk. So the main takeaways are threefold before we get started. So first, I hope to convince you that dynamical Chern-Simons gravity is a well-motivated theory that has promising cosmological and gravitational implications for observable windows. And then more specifically, I'm going to be talking about something we call the DCS Caps, which are these unique geometric structures which we recently found that DCS black holes possess that present some potential deviations from GR and again, potential observable consequences. And then lastly, I'll talk about superradiance, which is induced by DCS black holes, and show that there are, again, deviations from GR, and I'll speculate on some potential observable consequences there. So to step back and give you the big picture and the kind of, why do we care about this at all? I think of this work as a compilation under two main umbrellas. So on one hand, we have modified gravity, where by modified gravity, I don't mean kind of modified gravity in the Mond sense, but rather well-motivated theories from beyond the standard model or string theory perspectives that give rise to corrections from GR and potential observable consequences. And so on the other hand, we also have this really exciting era right now where we have access to a lot of different gravitational observables in these forms that I've written down here. And so we can now probe these modified theories of gravity using these gravitational observables in the same way that we, for example, can probe beyond the standard model of physics with terrestrial colliders. We can now look for beyond GR physics using these various avenues. And so what I'm going to be talking about is kind of in the middle here. So looking at these potential observable consequences in the context of both signatures and constraints. And so I also just want to point to some of my other previous work, not on DCS gravity, but in some other modified theories of gravity using different data analysis and theoretical techniques to look at some of this. And this is, of course, also many people work in this intersection as well. So before we get into all of the technical details, I just want to take a minute to distill down the essential physics that we're going to be speaking about. So as I said, we're going to be talking about these DCS caps as well as superradiance in DCS gravity. And so there's a nice intuitive physical analogy for both of these. So for the DCS caps, these are these geometric structures that are induced by the associated scalar field of DCS gravity, which I'll explain a little bit more explicitly in a couple slides. And this scalar field is maximized at the north and the south pole of the black hole. And so in the same way, that's where these caps are maximized. So we can think about this scalar field kind of dragging along the caps and leading to this amplitude here in the same way that we can think about angular momentum increasing from a minimum to a maximum if you're spinning, for example. So again, not a perfect analogy, but just a nice way to get some physical intuition for the system. So on the other hand, we have superradiance. And so one nice analogy here is to think about a harmonic oscillator with some that's oscillating at a resonance in some driven system. So again, if we have some system, some oscillating system that is oscillating at a resonant frequency, the amplitude is going to be increasing. In the same way, this is the kind of thing that happens here, where we have a system that is oscillating at some particular frequency that gives rise to increasing amplification. Again, not a perfect analogy, but just to give some physical intuition. So now to talk about DCS gravity. DCS gravity is characterized by the addition of the Chern-Simons term to the gravitational action. And this is a term that arises in string theory and effective field theory. So for example, the Green-Schwarz mechanism in string theory, this term arises as well as in effective field theories, such as this Weinberg example of the effective field theory of inflation. This term appears in lots of different pockets of physics and is extremely well motivated in that way. So DCS gravity is also parity violating due to the fact that the background scalar acquires this non-trivial profile. And this can have effects in both the early and the late universe. DCS gravity also includes a intrinsic axion-like particle. And so if we're thinking about modified gravity from, for example, a dark matter perspective and how we might be able to modify gravity to look at dark matter, this makes it an attractive potential avenue. And then just in general, there are many cosmological and gravitational and particle physics implications for adding this Chern-Simons term to the action and considering this modified gravitational theory. So here now I'm just going to talk about quickly some of the technical details of the theory. So up here, I'm showing the action. And so here, the first term in the action, first term is just the normal Einstein-Hilbert term, where R is the Ricci scalar, so just the normal action of GR. And then the second term is the Chern-Simons term, where all of the action, unintended, occurs. And so we have this curly theta here is the pseudoscalar field, which is an axion-like particle that is coupled to the Pontryagin density of the spacetime. That's this RR dual term. And then here, alpha is just a coupling. And then we'll also have a kinetic term for the scalar field. So this is the full action, vacuum action of DCS that we're going to be considering. And from this action, we find that there is a modification to the Einstein equations. So this is shown here. So we have the usual Einstein tensor and the energy momentum tensor, and then also a contribution from this C tensor terms. The CAB is called the C tensor, and this arises from directly from varying this Chern-Simons term in the action. And so we can think about this as a contribution to the effective energy momentum tensor of the whole system. And we can see that it's proportional to both the curvature and to the scalar. And so the scalar itself also has an equation of motion that's just a wave equation that is being sourced by the Pontryagin density of the spacetime. So what you'll notice here is that if the Pontryagin of the spacetime is 0, the scalar field will also be 0, and this whole thing just reduces back down to GR. And so this happens, for example, in spacetimes with high amounts of spherical symmetry. So for example, the short-shelled spacetime, this RR dual term is 0. And short-shelled itself is now just a solution to DCS because the addition of the scalar is 0. However, if we go to spacetimes with that break spherical symmetry.
Sorry, just to understand notations.
Yes.
Because this one over kappa in the equation, there's some mismatch between notations in the first line here.
Oh, yes. So here, kappa is just 16 pi. So,
sorry, that kappa upstairs, that's M Planck square, right? But this kappa in the lower equation where it's kind of.
I think, yeah, there's potentially a factor of kappa that should be in the.
So there is alpha over kappa probably in the coupling there, right? So alpha for you is a dimensionless number or?
Alpha has dimension 1 over mass.
1 over mass. Okay. Yep. And kappa is a M Planck square, right?
Yes.
So I think everything is written in M Planck equals to 1 units.
Right, so cap is one.
Yeah, but irrespective, there is a mismatch in kappa. There should be either kappa upstairs or no kappa downstairs.
Right.
So, but it's insignificant.
All right. Yeah, no, but just understand the units. So
But this is an M Planck equals 1 unit.
Thank you for catching that. Yeah.
Sorry, I got late. Sorry, but this other dual you say is the Chern-Simons term. I only know Chern-Simons as ADA plus the wedge of 3A's.
Yeah.
Here in this context, what is other dual? What is R basically? Or
Yeah,
R-
so that's a great question. So here our dual is the derivative, essentially the derivative of the Chern-Simons term. So you can write this as the covariant derivative of this ADA plus A wedge A wedge A.
Oh, so we have like gauge fields as well. We have gravity, the axial, and gauge fields in this theory.
So sorry, yeah, so this is the gravitational version. So I guess I suppose it's not A, but it's the connection of the metric.
Okay.
And in coordinates, it's like the Riemann tensor, but contracted with a later should be a symbol.
Right.
Yeah, so I can actually,
No, don't worry, don't worry.
I have an extra slide that's
Okay,
in
okay.
detail if you want to see after. Any other questions so far? Okay, great. Okay, so as I was saying, when we go to spacetimes that break spherical symmetry, such as a rotating spacetime, Chern-Simons is now not so trivial, and we have to consider this addition of the term in the metric. So the first individual DCS solution was found by Yunus and Pretorius, and they did a slow rotation expansion to find the solution. So what we'll see here is that this is a full metric. And so DSK is just the Kerr metric, so normal Kerr metric of GR. And then we have this correction here. And so zeta is a dimensionless expansion parameter, which is proportional to alpha in the metric. And then here chi is just the dimensionless spin parameter of the black hole. And so this solution is found in an expansion of zeta and chi. And so here I'm just showing the leading order correction, but this solution has been extended by these other groups up to fourth order in the spin. And I don't have 5 slides to show you the full metric. But at the higher orders in the spin, there are corrections to all components of the metric. This is just the leading order term, just to show you the example.
Sorry, chi again. What's chi?
So chi is the dimensionless spin parameter. So if you take A, the angular momentum parameter for a black hole, and divide it by m, mass of the black hole is chi. And so this solution also has a non-trivial scalar field that's associated with it. And so that's again shown here. And you'll notice that this is proportional to cosine theta. And so it's maximized at the north and south pole, which becomes important for the caps, which I'll speak about in a moment. And the solution also has deviations from the Kerr metric in terms of the location of the horizon and the ergosphere. So it's again just shifted. K's just denote the location of these quantities in Kerr, and it's just shifted by some slight amount proportional to zeta and pi.
What's curvy theta?
What's what, sorry?
What's the second term you write down, which is kind of curvy theta?
Oh, theta.
Yeah.
So theta is the associated scalar field that comes along with the solution. So that is this theta here.
Okay, thank you.
And zeta is linearly proportional to alpha?
Alpha, zeta goes like alpha to the 1/2.
And M here is what is.
M is the black hole mass.
Is that theta the vacuum excitation factor of the field, or is it because it's just a dynamic in theta?
It's dynamical in theta.
Yeah, just I can't understand because I'm a bit confused. If alpha were the one in Planck units,
One expect these corrections to be kind of suppressed because it's some Planck separator. But here it looks like R plus minus is it was R plus minus for Kerr is itself for the M. So zeta over the 1, chi over the 1, it looks like it's over the 1 correction. to the
So
Kerr method.
zeta has to be much smaller than 1. Is this slow rotation expansion?
Sorry, chi slow rotate.
Zeta has alpha.
So, yeah,
So that's the separation.
but if alpha over the 1 in Planck units, right?
That's a Planck scale. Then your term is over the Planck scale.
So this mass, yeah, so R in these notations, in the units, R plus minus of Kerr, what is it? It's for the M, or because usually So for the M, right? So that's
Yeah.
the horizon size is
That's
for the M.
For sure.
And zeta then is dimensionless quantity. So it's quantity order 1.
No, it's more.
Why? Well, let's take alpha order 1 in Planck units, right? Then wait in some dimension 5 operator to our theory. Well, yes, the 5-dimensional operator series suppressed Planck by Planck scale. So we expect the corrections will be very small.
Well, why do you expect them to be small? I mean,
Well, because I
in
had
this
Planck
modified theory, I mean, nothing is small.
No, I had a Planck suppressed operator, right?
Yes,
I did operator
I-
suppressed by Planck scale. So I expect for a large black hole, it should have very small effect.
But alpha is not 1. If you converted alpha, if you restored the dimensionalities, alpha would be something like 1 divided by F Petri queen times M Planck or something like that. So it's a more involved conversion from dimensionless to dimensional unit term.
But let's take it order 1, right? Let's take alpha order 1 over M Planck, like in Planck units, order 1 in Planck units. Then it looks to me the initial action. It has some Planck suppressed operator.
Yeah, this will be Planck suppressed as well.
But here I don't see Planck. Yeah, there's a problem. In this correction, I don't see Planck suppression because it looks like M. It looks like
when you restore, you will see. When you restore in Planck, they'll be in Planck suppressed.
Yeah, so maybe, so zeta, if I'm remembering correctly, is proportional to 1 over G M to the 4th. alpha.
sorry, zeta itself, it's not just A, it depends on the
Yeah,
mass.
so it's
Okay.
proportional to alpha squared, but there's, once you restore.
It's not
units,
just
there's-
alpha, there is a black, okay, yeah, perfect, that's.
Yeah, so probably to get an order 1 effect, the scale suppressing the point of grain density has to be of order.
Right, yeah, right, it should go for the
size
black
of
hole
the
size,
black
right,
hole.
yeah, right. Okay, no, I thought that zeta is just something for the alpha, but yeah, there is mass there, yeah.
Yeah, so we had a long discussion about this with different units and matching things.
No,
So,
thanks.
good
Yeah,
question.
Yeah.
Okay, any other clarifications?
In a similar way, you have the modification of the ordinary Schwarzschild solution and, for instance, Northern-Eisner, or it's only for the Kerr that you can have the explicit solution for.
Yeah, so in the case of Schwarzschild, because the Pontryagin is 0, any correction and the scalar field is also going to be 0. So in that case, it's been, you can show it explicitly and it's just going to reduce back to GR. So in order to get this Chern-Simons correction, you need to have a non-zero Pontryagin. So in this case, the next simplest thing to do past Schwarzschild is to look at a rotating black hole. Okay, so this brings us now, sorry, was there another question? So this brings us now to the Chern-Simons caps. So to motivate the caps, I want to write again the Einstein equations in a slightly different form. So this is now in the trace reversed form. And I put the C tensor onto the right-hand side of the equation. And I've done this on purpose because now we can see that there's a minus sign there, which may seem very obvious. But the importance of this minus sign is that this quantity on the right-hand side of the black hole is now no longer positive definite. There's no reason why the C tensor term is necessarily going to be smaller than T here, and T bar is just the trace reverse form of the energy momentum tensor. And so the right-hand side of this could potentially be negative. And so this is important because of the geodesic focusing theorem, which I've shown here. So if you have the Ricci tensor and you contract it with 2 either null or time-like vectors, so here U is either null or time-like, and that quantity is greater than 0, if you have a congruence of geodesics, they're always going to converge. And so this is very important, for example, in the singularity theorems and other important results in GR. And what's important in GR is that this quantity is always positive. So assuming that the strong energy or null energy condition is obeyed, this quantity is always going to be positive, and therefore you're always going to have this geodesic convergence. So now in DCS, because we have this additional term, this minus sign, that's not so clear anymore. And so we see that, again, we haven't made any sort of assumptions here, or we haven't picked a particular background. This is directly from the theory itself. And so we see that the DCS gravity as a theory just generically has this feature that we can potentially have violation of the focusing theorem.
Is it something special to DCS or generic property of some high dimensional, right? Some other high dimensional corrections will be.
That is a good question. So I think it obviously it clearly happens in DCS. In terms of generic higher dimensional corrections, I think that would be dependent on the specific form of whatever kind of higher dimensional operator you're considering, and whether it works out in this case that it has the particular dynamics where we get the C tensor. But I can't say whether that would be generic for all of these types of corrections.
And here, does it depend on the sign of alpha, or is it for either sign of alpha that you could find solutions where you violate the focusing inequality?
So here alpha is going to be positive.
Yeah, I have one naive, but you said it's modified gravity, so this term seems to be smaller. So why do we still violate?
I will show you that on my next slide.
Okay. And also, will they have provide some non-diagonal term if we do, if we do the composition in some, I mean, for a stable observer.
Some what, sorry?
Some stable observers which go around with the black hole. I mean, if TAB just have the diagonal terms, so we'll see if it provides some non-diagonal.
Sorry, can you repeat your question?
Yeah, sorry. So I mean, you know, if I mean the simplest case of the TAB is just a row PP, right? Well, CAB provides non-diagonal for this.
Oh yes, CAB is off diagonal.
Oh, off diagonal. So then, I mean, then if we choose the UA in this direction, then we provide. Oh,
Right.
okay, thank you.
Yeah, that's perfect.
But TAB is also dynamical
Oh,
because it's a self-contained solution, right?
thank you.
Okay, so if now the next question is to say, well, this has this generic feature, but does this actually happen? And so the answer is yes. So if we take the slowly rotating solution that I flashed up earlier, up to all orders in the metric, so up to fourth order, we find the following, and if we consider a time-like stationary observer. So here, there's just some shorthand here. So F is just the Schwarzschild factor, gamma is just M over R, and then C theta is just cosine theta. And we can see that this whole term is positive definite up until this last term here, where we do have a minus sign. And we calculated the zeta chi to the fourth correction as well. Again, for the sake of space on the slide, I won't put that up, but it obeys, it has a similar kind of form. And so this minus sign, when we look at the full dependence of the solution, we find the following, and this brings us to the Transcendence Caps. So here on your left, we have a slice at theta equals 0 of a black hole, looking at the magnitude, or looking at the value of this contraction. So this RAB contracted with two vectors. And so we see that this is to both orders in the spin. And we can see that there's a region here. So this cutoff here is the horizon. And then going out to about R is 2.06 M. We have this region where this quantity is actually negative. And so then if we extend that to all angles here, we see this cap-like feature emerge. So here on the right, the blue region is the region in parameter space where this quantity is negative. So we can see that it's maximized at theta equals 0, going out to R is about 2.06 M, and then it dies off to about 20 degrees on either side. And we have this cap-like feature at the north and the south pole of the black hole.
Sorry, I'm not familiar with all this. For example, you said something of that theorem and something about the geodesics. Can we understand that from a Penrose diagram of your metric? For example, if I draw an observer and I know in a black hole what should happen, can I get that behavior of writing kind of the conformal version of your metric and see what observers do, or it has nothing to do with real geodesics on the space-time. This behavior of this theory has if I draw the word line.
Yeah, so I'm not as familiar with that formalism, but this is, I think if you were to look at the behavior for null geodesics, which is something we also did just in a numerical sense, you can see this behavior. What we actually found is that they don't, they slow down. If you're looking at geodesics kind of going into a black hole,
Yes.
they slow down in relation to the GR counterparts. But they still overall exhibit mostly the same behavior for the null geodesics.
But we do have an event horizon, I guess. So eventually they will.
Yeah.
Ah,
Yeah, so this isn't saying that the singularity is going to be avoided. I'm definitely not
okay.
saying that, but it just has this feature,
Okay.
which can be related to energy conditions and so on, kind of behavior of the caps. Okay, so we now have these caps, and we can think about some potential implications. So again, here I'm just drawing this little cartoon. This is not to scale, but just to show you an example of the geometry of the system and to give you some physical intuition for the size of these caps. If we were to consider the rotating black hole at the center of the M87 galaxy, which was recently imaged, of course, by the Event Horizon Telescope, that black hole has a mass of about 6 billion solar masses. And so the largest extent of these caps is going to be about 3 astronomical units, which is about the distance from the sun to the asteroid belt. So kind of like inner solar system scale regions are what we're seeing here.
For what value of parameters? So here you're taking this zeta to be.
Yeah, so here we're taking zeta is 0.1 in this zeta is much less than 1, and then we're also taking pi is 0.1 for the value of the spin.
So that's a huge Chern-Simons.
Yeah, and so what is actually interesting here, that brings me to another point, is that for whatever values of zeta and pi and the couplings that you're considering, the size of this region doesn't actually change. So it changes the overall kind of amount of negativity, but the overall size of the region stays the same. So even if you had a different choice of the parameters, this still exists.
What is the constraints on this zeta from like this gravity?
So zeta is quite poorly constrained from observational perspectives. So in terms of, we're just taking it to be, zeta is 0.1 as kind of an example choice for this, but the overall constraints on zeta are not that good from observations. They're quite mild.
But because this is the theory, like what is the cutoff of this theory? Because it's some high-dimensional operator and take suppressed by some very low energy scale, but they told the one for M87, right? So what is the resulting cutoff, which corresponds to that value of data?
So I think the cutoff depends on, from an effective field theory perspective, I'm not sure off the top of my head what that would be, but I will look into that and get back to you after the talk, if that's okay. Okay. All right, so as I was saying, we have these caps, the kind of solar system scale regions. And as I was mentioning, so for some potential implications of these are in terms of this negativity of this contraction. So again, we still definitely have a singularity in this black hole. The Hawking-Penrose theorem is not violated in this case. But we do have these regions where we have something kind of funny going on with the energy conditions. So thinking about how those types of regions might interact with matter, for example, to give us a potential observable effect is the next type of step. And so this brings us, this has motivated us to look at superradiance in this theory. So we were wondering if the presence of these caps would would have an impact on the presence of the superradiant instability. And I'm going to kind of spoil the punchline a little bit and tell you that they actually don't. We found that the caps are not actually related to the superradiance, but it's still looking at superradiance in DCS is still an interesting problem in its own right and gives us some deviations from GR. So as I mentioned before, superradiance occurs when we have a rotating black hole with some sort of external scalar field that's associated with it. And due to the rotation of the black hole and interactions with the ergosphere, the amplitude of this scalar field becomes magnified and increases, giving rise to this black hole bomb effect, as coined by Press and Tucholsky. And then it gives rise to these kind of two clouds emanating from the equator of the black hole, kind of in analogy to a hydrogen atom. And so superradiance in general is a powerful probe of hidden scalar sectors. People have used it in terms of axion dark matter to place constraints in that regard. And we're going to now use it as a probe of modified gravity and see how in DCS the superradiance process is altered in comparison to GR. So first, I just want to review the basics of superradiance in GR. And so we're going to consider some massive scalar field, which is on a rotating Kerr black hole background. So we just have the Klein-Borden equation. Mu is going to be the field mass. And then phi is just the scalar. And so in order to solve this equation analytically, we have to do it in some sort of limit. So we're going to follow the methodology first done by Stephen Detweiler in his original paper from 1980. And so he looks at the low frequency, low mass limit here in order to make this equation separable. So you can solve it exactly, but you have to do it numerically. So in order to find an analytical solution, you need to either take this limit or the opposite limit, which people have also done. And so here we can then make an ansatz for the solution of the following form. It separates nicely. And so here, this SL, the angular dependence is just going to be a Legendre polynomial. It's going to be a PLM. And then we'll see that the superradiance comes from the first term here. So if we have the frequency and the frequency has a positive imaginary part, then this whole thing is going to be exponentially growing, and that's what gives rise to the superradiance, the superradiant instability. So if we take this solution and then skipping a whole bunch of technical details, which can be found in Detweiler's paper, we can look at the frequency spectrum of the scalar. And this full solution is actually a sum over all modes, but the dominant one is going to be the L equals 1, M equals 1 mode. And the imaginary part of the frequency is shown here and is proportional to mu m to the 8th. So the mass of the scalar to the 8th. Quite a small correction, but on long time scales, it can have a big effect and gives rise to the superradiance. So now we can turn to looking at superradiance in DCS. So just to set up the scenario really quickly, we're going to take DCS gravity and then add an additional scalar field. So the full theory is going to be given by these first three terms, which are just the action of DCS that I showed earlier. And then we're going to consider another scalar field, this phi, which has the following action. So I just want to clarify that we're not actually looking at superradiance of the DCS scalar. We're considering the black hole plus the DCS scalar plus some other scalar, and then that's going to be having the superradiant instability.
Just can I ask, why is that? Why not give a mass mu to the theta scalar?
So the theta scalar, that's a great question. So the theta scalar, when the Chern-Simons term gets derived, is Planck suppressed. So it's the mass has to be very, very small. And so in order to see a wider range of the superradiance, we're going to just consider this other scalar, which makes things kind of less constrained. We're allowed to consider a wider range of masses. But in principle, you could look at superradiance of the Chern-Simons scalar, but we just chose to consider it separately. Okay, So now we'll go through those same steps that I just described for superradiance in the GR case for the DCS case. So we're now going to have the Klein-Gordon equation. We're going to take that rotating, slowly rotating solution up to second order in the spin. And so that's going to induce a contribution to the D'Alembert operator. And since this equation is rather messy, we're going to solve this perturbatively. So we're going to consider that the solution is mostly Kerr, and then there's going to be some small DCS correction that's going to be proportional to zeta. And so we'll make the same ansatz, and we'll say low frequency, low mass, and then we'll take the same limit, and then we'll make the following ansatz. So the way that this equation separates, we actually get a linear combination of multiple modes. So in this solution, we again have the sum over all modes. We have the Kerr GR solution, and then we have the DCS correction that is as follows. So we have, in addition to the PLM correction that we're seeing from the PLM contribution of the GR, we also have additional contributions from the L+2 and L-2 modes. So for every L, we have these 3 contributions to the DCS part. And so again, skipping many technical details, we do a procedure of matched asymptotic expansions, and there are some subtleties when we have to consider the metric near the black hole. Then you can find all those details in our paper when it's out very soon. We can again look at the frequency spectrum, and we can see that the L and the L+2 modes are going to be maximized for L = 1 and M = 1. So this is the same as for GR. And the L-2 mode is going to be maximized for L = 3 and M = 1. So to look, yes.
So the theory is characterized by the fact that parity is violated. In the solution for the scalar field or in the form of the theta before, do you see any trace of this breaking parity?
So I think you can see that in the actual solution, like with the metric and the scalar, but in this particular formulation for the scalar, I don't think the parity violation really appears.
Would you expect to see a parity violation in the form of the solution, or
Not necessarily here. If it was going to appear, I suppose it would appear in the radial components. But here, because we're considering this additional scalar that's kind of on top of the black hole, I wouldn't necessarily expect it to have parity violation.
Parity is not violated, right? The state is pseudo-scalar.
Yeah.
The series parity invariant.
Yeah,
well, it was written explicitly that it's parity violating.
No, because theta just transforms to -8 under parity.
so the term itself is parity invariant.
So the theta is
Because it's product of 2 pseudoscalars. Of course, you give a web to a pseudoscalar in that respect, it's violated, but it's like, nonlinear spontaneous report in parity term. So.
But that also happens just
That's right.
in the standard case.
Yeah.
Okay. So if we now look at the frequency spectrum, here I've plotted L = 1 and L = 3. So again, this is looking at the imaginary part of the frequency for L+2 and L-2. So again, there's going to be in the full solution, there's a sum over all the modes, but we found these are the dominant ones. So we're just going to look at these. So here the solid line is L = L, the dot dashed line is L+2, and then the dotted line is L-2. And so what we can see here is that it's basically the P11 term that is highly dominating the solution. So, or is the most dominant frequency. So I'm not sure how well you can see this, but this is a log scale. So these other L's are significantly suppressed in comparison to the basically L = 1 part.
So the solid lines there on the left panel, that's the usual one without the DCS term? Or
So this is all just the DCS part. This is just looking at the contributions for the like omega L, omega L+2, and omega L-2. Yeah, So, but this solid one up here matches with the GR one. So this is what you would get just in GR, and then in DCS, we have all the other corrections as well. Okay, so even though these other corrections are small, we also want to look at the angular dependence of the scalar field to see how it might be altered due to the presence of these other modes. So we can go ahead and do that, and we'll take some example values for all the parameters, and we find the following here. So here I'm plotting just the magnitude of the field as a function of theta. So you'll recall that in the GR case, the scalar fields have this characteristic kind of lobe-shaped behavior. And so we can see that here. So here the black is the GR and the red is the DCS. For again, L equals 1 and L equals 3. And this whole thing is very highly dominated by the L equals 1 GR contribution, which is what we expect because again, we're solving this perturbatively and we expect the DCS part to be suppressed. So the overall behavior of the cloud is still going to mostly follow this L equals 1 GR part. However, we are going to have these other contributions that will add up, and in a potential observable sense also will maybe have some implications.
Sorry, but this shape looks very similar on the computers, but when for left panel, the DCS is just some kind of order of magnitude smaller behind it, but they have similar.
Yeah. Yeah. So here, as I said, so the overall shape of the cloud is going to be the same, but there are going to be kind of this like infinite. If you consider multiple modes, you are going to have these other corrections that add on top. So here, it does happen to be that this kind of P11 shape is the one that's dominating. So in the overall shape of the cloud, it's going to be the same or very similar, but there's going to be the addition of these other modes. There may be some ways to differentiate.
The reason the L equal 1 is same to L equal 3 is because for the wave function you have L minus 2 contributing to the 5.
Yeah, exactly. And so that one is
It's pretty similar to L1 having L3. That's
right.
Right.
Exactly. Okay, so just to follow up on your question, even though the overall kind of angular behavior of the cloud isn't that drastically different, there are still potentially some avenues where we might be able to look for observational consequences. And so we can look for example, gravitational wave emission from the black hole that's interacting with the cloud. People have done this for scalar superradiance. And so now, because we have these additional contributions to the cloud, there would most likely be some distinction there. We can also look at the spin down of the black hole. So as the scalar cloud becomes increasing and gets radiated out, it's taking angular momentum from the black hole. And so there are nice constraints that you can place from the mass of the black hole and the spin. And so that's something that people do, and definitely a direction that we are going to be pursuing with this. And particularly also looking at people in the past have used these tools to constrain the scalar sector, but nobody has really looked into using these particular tools to constrain modified gravity. So in that direction, we can constrain DCS. So some other potential directions that we're thinking about in terms of future directions are looking at fermionic superradiance. So in GR, fermions have been proven to not exhibit superradiant behavior. This was proven by Unruh and then verified by others. So if we were to be able to find superradiance for fermions in DCS and then be able to find some observable signature, that would be kind of a smoking gun of DCS, which would be very exciting.
But sorry, but what they mean here? Because I thought just Pauli principle, because what makes fermions interesting is that, like laser type state, but for fermions you cannot have anything. So how is DCS?
Right.
We'll get around this.
Yeah, so this is the kind of the next thing we're pursuing, but the idea is that hopefully if there is some way that given the addition of the scalar and the caps, potentially one might be able to evade those same arguments that apply in GR to get some sort of behavior for the fermions in DCS.
But you won't get fermionic cloud.
Yeah, only if you have some condensation, like DCS type condensation. Still, again, it boils down to the scalar example, but there's some additional dynamics.
And then the last thing that we're kind of thinking about is other ways which we might be able to consider, for example, some other scalar interactions to amplify the DCS contribution to see if there's a way to make it less suppressed compared to the GR to pursue it that way. So then I would just like to summarize and conclude. What I've discussed today is that DCS Gravity provides this vast background to search for observational signatures of modified gravity. And I've kind of shown some work that's moving in that direction to set the foundation for looking for these signatures or constraints in DCS with both the DCS caps and with superradiance. And there's certainly more work that is very necessary that we will be pursuing in the near future. And with that, I thank you so much for your attention, and I'm very happy to take any questions.
Yeah, any questions?
Yeah, so I have one question about DCS. You said the such kind of DCS the angle is around 30 degrees around. I mean, so it is for any small value of alpha, as long as there's such kind of modified variable, or it depends on alpha actually.
So the size of the caps is independent of alpha.
Okay, so but maybe the thickness of the cap will depend.
Yeah, so the thing that changes is the amount that that region is negative. So if we were, so again, thinking about kind of the energy conditions and this kind of weird matter or the way that the space-time is behaving near these. So the amount that that differs basically from GR is dependent on alpha, but the actual region size is not.
Thank you. There's a question by Yifan. Yifan, speak up.
Thanks for a nice talk. So just a question. So in the usual Einstein gravity for Kerr black holes, if you zoom in onto the horizon, there's this interesting emergent CFT, the two-dimensional Kerr CFT. This is known as the Kerr CFT correspondence, developed by Strominger and collaborators. So what I was wondering here is if you include this additional Pontryagin class coupling, what is the signature of that from this 2D CFT perspective? Is there some kind of natural deformation you can consider from the usual Kerr CFT story?
Yeah, thank you for that question. That's very interesting. I haven't thought too much about this from a CFT perspective. I know you can do a dimensional reduction of this metric to look at it in like 2+1, for example. But I am off the top of my head not sure what that would look like in terms of a CFT conformal field theory kind of signature. But that's definitely something interesting to think about.
Yeah, it's a two-dimensional CFT in this case.
Okay, I see. Yeah, that's an interesting point. I'll think about that. Thank you.
And if I can ask, so how much of your story changed if you consider instead of on flat space? Well, so sorry, with zero cosmological constant, consider the case when you have say negative or positive cosmological constant.
So in this case,
How does the de Sitter or anti-de Sitter solution change once you include this additional coupling?
So that is also a good question. So I don't think that de Sitter or anti-de Sitter like solutions with this Chern-Simons coupling have been found in this theory. I think that's something that you could do numerically. But I think in terms of an analytical solution, I'm not entirely sure what that would look like. But I think that if, in general, if you consider the addition of a cosmological constant, when people have done this in GR, for example, for superradiance, for small values of the cosmological constant, I think if I'm remembering correctly, it doesn't change the superradiant behavior that much. So I would imagine that those same arguments would apply here.
Okay, thank you.
Yeah, I was curious about the, so you said these caps don't violate the Penrose focusing theorem, and you confirm that numerically? Is that right?
Yeah, so we just, by numerically, I mean, we kind of just plotted the ingoing geodesics in this case versus Kerr. And so in looking at the geodesic equation here, even with the addition of this Chern sign, or the C tensor term and the minus sign and everything, in the region of the caps, they still do, you know, hit the horizon, is what we found numerically, but they do slow down in comparison to Kerr. And so our thought on that is that because even though these regions are quite large in extent in the way that we're thinking about it, obviously in terms of a black hole, that's going to be quite small if we think about like a geodesic incoming from infinity, for example. And so potentially if the caps were larger in some way, it might have more of an effect, but it doesn't seem to generally change the overall behavior of ingoing null geodesics.
Yeah, so I was curious about like, for instance, if that profile wasn't like a cap, if something happened, like two black holes, for instance, collided or something, I don't know, there's some wiggles that form. Is there a general argument that you wouldn't get violations of this singularity theorem or something like that? Like, is it just the fact that the coupling here is so small that you're taking this sort of like derivative view? I don't know if there's maybe some complicated geometry that could form in the scalar field profile that would.
Yeah, so I think that that's certainly not outside the realm of possibilities. Like if you did have some, you know, collision, and you could either kind of amplify this geometry or deform it in some way, then maybe you could get a different result. There isn't anything kind of, I guess, yeah. The case that we looked at to show this was just kind of a standard case for ingoing geodesics, but I think if there's nothing globally to say in general that you couldn't have some sort of other configuration where you could get a different result.
Any more questions from room or online? Okay, now let's thank Leah again.